Hi everyone and welcome back to PrepFusion. I'm Anish and today we'll start with the lecture 13 of our chapter 1, that is transformers. So today we will discuss about effect of frequency in transformers and losses in transformers. Okay, so let's discuss, right? Let's discuss about frequency. So we know one thing, that if my VRMS is fixed, then I can directly write this induced EMF voltage equation. So E1 RMS will be equals to root 2 pi f phi m into N1. Okay, so this is the RMS voltage. Now one thing we comment, that my maximum flux, right, maximum flux in the core is actually dependent on the ratio of the voltage E1 RMS, which is roughly equals to proportional to voltage upon frequency, because other things will be fixed, right? So it is proportional to V1 RMS only, the supply, because assuming winding resistance to be negligible. So now if I am operating in low frequency region, that is my initially my, let's assume that my V1 RMS is 240 volts and F is 50 hertz. Now if I change my F to F dash, that is 25 hertz, what will happen? The flux, right, phi m dash will be 2 phi m. You can simply take the ratio here because it is inversely proportional to frequency. So if frequency reduces, flux will increase twice. So flux has increased twice. So I know one more thing. What about the flux density? Bm dash. So Bm dash is basically phi m dash divided by area. Area is fixed for the core. So Bm dash also will be twice of the initial flux density. Okay. This can cause a problem. What kind of problem? If you remember, my BH curve was something like this. This is my BH curve. So in the BH curve, if you remember, the hysteresis loop was somewhat like this, right? If you remember. So I mean, it was somewhat like this. So initially my BM was here. I was lying here, but my flux density has increased. So I am lying here. So this is my BM dash, twice of BM, correct? So this is a problem. Saturation, right? And we know that in saturation, harmonics, all those things are there. So it's not like I can reduce the frequency very low. That is a problem. That is one problem. And also your magnetizing current also will increase, right? Initially my IM was here, my IM dash is here. So magnetizing current also will increase, which will increase the core losses. So from this, the core losses also will be increased. Hysteresis and eddy current loss. So if I change the frequency, lot of things changes. Okay. So we have to be very careful. We cannot just blindly change the frequency. Okay. So for low, all this happens for low frequency. So the conclusion is, if we operate in low frequency region, the magnetizing component of current increases. So if frequency decreases, the magnetizing component of the current will increase. So there is a problem, right? There is a problem. Okay. So what we can do, if we want to keep the same magnetic flux, right? If I want to operate the in low frequency, and if I want to keep the same magnetic flux density. So this was for the first one. If the area is area is constant. So here area of the core is, area of the cross section of the core is constant, A is constant, that is area is constant. In case 2, what if I make the area variable, I change the like I make Bm to be constant, Bm is constant, okay. I want the flux density in the core to be constant so that the magnetizing current drawn should remain same, okay. Then what will happen? Flux phi m will increase, phi m dash will be 2 phi m only, okay. Phi m dash will be 2 phi m only. So what is Bm dash? Bm dash is phi m dash upon area, okay. Yeah, phi m dash upon area. So phi m dash will increase and I want to keep my Bm dash same. So what I have to do? I have to increase my area, okay. So if I want my Bm dash to be equals to Bm, that is equals to phi m by A. So here it is equals to phi m dash by A dash. This will be A dash, right? Because I am changing the area as well. So this will be 2 phi m divided by 2A. So from here I can directly say that my A dash, sorry, this will be A dash only, divided by A dash only. So A dash will have to be twice of A. So I have to increase the area of the cross section if I want to keep my maximum flux density same. So there are two things. Either you, so I will write here, that either you, like either you keep the area of the cross section same, then your core losses will increase, your magnetizing current will increase. But if you want to keep the same magnetizing current, that is you don't want to change this Bm dash, so you have to change the area of the core. So if we change the area of the core, that means in the case 2, if we want to keep the magnetic flux density constant, then what we have to do? Then basically we have to then area of the cross section of the core must be increased, okay. That is the only thing, that is the only solution. Now what about, this was about the low frequency operation, okay. So this was about the low frequency operation. Now let's discuss about high frequency operation. So what problems we can have at high frequency, okay. So let's now discuss about high frequency operation. Okay, so in high frequency, basically frequency will increase. So let's say now initially these were my values like V1 RMS and F dash RMS, but I'm increasing it. So initially it was 50 hertz, so my F dash currently is 100 hertz, okay. F dash currently is 100 hertz. So F dash currently is 100 hertz. What will happen to the flux? So basically my phi m dash will be twice, correct? Sorry, not twice. So phi m dash will be phi m by 2. It will get halved because it is inversely proportional. My phi m is inversely proportional to Vm or Vrms, V1 RMS upon F, right? So phi m dash will become phi m divided by 2. Flux will get halved, okay. So if flux is halved, then for the same core less magnetic less magnetic flux is required, hence flux density will be lower. so it draws less magnetizing current. Okay, so what I can comment is that because flux has been halved, that means I will require less magnetizing current. So if I draw my BH curve, so if flux has been halved, and case 1 is the case for which area of the cross section is constant. So I will write here case number 1. So where area is constant, area of the cross section is constant. If I write the BH curve, draw the BH curve, H is here, B is here. So this is my BH curve. So this is basically the uh, like initially my phi m was somewhere here. Okay, initially my phi m was somewhere here, and this was the magnetizing current required initially, but my phi m has been reduced to half, so I will be lying somewhere here. Okay, this will be basically phi m divided by 2, and this will be basically Im dash. So magnetizing current will reduce. So here I can write, what I can comment is that to for over frequency operation, uh, the magnetic flux density also reduces if area is constant. Flux density reduces, hence the magnetizing current required will be lower for same transformer core. Okay, so that was about the high frequency operation. Now if you want to keep the flux density constant, like there is advantage if I want to keep the flux density constant. If I want to keep the flux density constant, that is I want to, let me keep it here, that is I want my flux density to be constant. What will be the advantage that I will get? I will tell you. The advantage is, if I, let's say I want my Bm to be constant. So if I want my Bm to be constant, that means my phi m dash is what? Phi m dash is equals to phi m by 2. So what is phi m dash? Phi m dash is basically Bm dash into A dash equals to, this is Bm into A divided by 2. Okay, so from here I can directly say that this will be Bm dash into A dash, and this is Bm into A. So I want, like, my flux density will be constant, that is Bm dash will be equals to Bm, so A dash will become A by 2. So basically, right, what is happening, the area of the core that I require is halved. What I know this thing, that the weight of any material will be proportional to the density into the, this is density into the volume. And what is volume equals to? Volume is length into area, something like that, right? So volume in turn is proportional to area. So the weight is actually proportional to the area. So area has been halved. So if frequency increases, area has been halved. So what I can comment is, weight of any transformer is inversely proportional to frequency. So a numerical can be asked like this. Okay, if let's say I have increased the frequency and I want to keep the flux density constant, how much change there will be in weight? So weight is inversely proportional to frequency. If I keep on increasing the frequency, the weight of the transformer will change basically. Okay, so that was about the weight of the transformer. Okay, so you might have a question, sir, at high frequency why does the actually the flux reduces? Why does the flux reduces if I have an inductor? So if I have an inductor, right, what happens? The flux flows like this through the coil, right? Flux, direction of flux is like this. Okay. Now in inductor, there is a term known as interturn capacitance. Interturn capacitance. There is a term known as interturn capacitance. What is interturn capacitance? So whenever like there are two wires, so here, right, what is happening? The coil is like this. Coil is placed like this, right? So what is happening? There is air between these two wires, and whenever there is air, air is a dielectric medium. So basically a interturn capacitance will be formed between these two wires. That's why it is called interturn, because between the turns there is a capacitance, because air is a dielectric medium. So all these are like this only, like this only. So at high frequency what happens? At high frequency what happens is that this is what? This is 1 by omega c. So omega increases. If omega increases, this impedance reduces. So most of the current flows through here rather than here. So the magnetizing component of the current flows through the windings, correct? Im. So of course, if the current is getting some low resistive path, that is this one, this is known as the IC current. So what will happen? Basically it will flow through the capacitor only, because omega is increasing, so this impedance will be reducing. So more of the current will flow through here rather than here. So Im is reducing. If Im is reducing, flux will reduce. Okay. So that was the reason that due to that the flux is lower at high frequency operation. Okay. Got it. So my IC will be greater than IL. Very larger than IL. So if IC is very larger than IL, so my flux obviously will reduce, because so not IL, sorry, IM. So my flux will reduce. Magnetizing current is reducing, flux will automatically reduce, because again the BH curve, right? If you remember the BH curve, that this is H, this is B. So this is proportional to I, this is proportional to flux. So if of course if I reduces, if I'm here I is reducing, then of course the flux will also reduce. Definitely flux will reduce, right? Got it? So this, remember this air, like why is this interturn capacitance here? Due to air. Okay, air acts as a dielectric. Okay, so this is known as the interturn capacitance. Got it? Okay, so whatever we had discussed, that is actually written over here. So effect of frequency, what happens if you operate at low frequency? So magnetizing current will be higher. Okay, that is why transformer are not designed to operate below their rated frequency. So we rarely operate transformer below their rated frequency, because the magnetizing current will increase, everything will increase. So we don't use it at low frequency operation. To compensate the increased flux density at lower frequency, we can reduce the core area as discussed, cross sectional core area. Okay. So high frequency, when frequency increases while keeping the same core, the required magnetic flux increases, as flux is inversely proportional to frequency. The lower flux density means core does not need to draw as much amount of magnetizing current as previously. And however, at high frequencies, skin effect and proximity effect in the windings become very significant. So we discuss about skin effect later on as well. Okay, so these actually increase the copper loss, because more current is flowing through the interturn capacitance, so less amount is flowing through the windings. That was for the magnetizing current, but this kind of losses are also there. It's not like you will always be able to use it at high frequency. It's not always. It is mostly used to operate at rated frequency. That's why you will never see that transformer is operating at some other frequency than rated frequency, because that is the optimal value for which it is designed for. Okay, but of course what will happen in high frequency, that we have discussed. So what are the applications? Low frequency operation, like not low, 50 hertz operation are generally used for power transformer. So whatever power you are receiving at your homes, everywhere else, and how whatever power we are generating, in the generating stations are of 50 to 60 years, and for those kind of applications power transformers are used. So typically designed for a specific frequency. Okay, so now in aircraft and military operations we use high frequency transformers. So it allows smaller and lighter cores because high frequency area will reduce. Okay, I have discussed how area will reduce. If area reduces, the weight reduces. Okay, and there can be bit of variation here in the frequency. Losses will not vary much. Okay, and also induction heating transformer are also used for much higher frequency like kilohertz range. Okay, this you will study in BTech. If someone is studying electrical engineering, they will study this. Okay, somewhere some subject they will study. Okay, that was about the high frequency operation. So let's solve a few questions now. So this is the first question. For a specified input voltage and frequency, the equivalent radius of the core of a transformer is reduced by half. So specified voltage and frequency. So in these kind of questions, right, always write down what is changing and what is not changing. So always write down the initial values, initial and final values. Okay, so here my voltage is not changing, my frequency is not changing, but my this is same only. So my v dash is v, so my let me write this here only. Okay, v dash is v, f dash is f, but radius is getting halved. So what will happen to the area of the core? Area is pi r square, area is pi r square of the core cross section. So area will be basically 1/4. Very important point, area will be 1/4. Now what next they are telling me? They are telling me that the factor by which the number of turns in the primary should be changed. So number of turns in the primary, that is n1, should be changed to n1 dash, so that to maintain the same no load current. So no load current comprises of two things, IC and IM. Assumption is they have not mentioned anything, so I will assume IC to be 0, the core loss component, right, to be 0. So my IO will be approximately equals to IM. So basically the no load current, that is the magnetizing component of the current, must not change, should remain same. So how will this happen basically? So here what I can say is, what is the voltage equation? Voltage equation V1 RMS is root 2 pi f phi m, root 2 pi f phi m n1. This is my V1 RMS. Now what more I know? That they are telling me that the magnetizing component of the current must not change. Okay, so what is my flux equals to? Flux is equals to, if you remember, mmf upon reluctance. So it is n1 into Im upon reluctance. Reluctance is L upon mu A. So basically, right, this Im must not change. Im will be constant. Im is constant, and this V1 RMS is also constant. F is also constant. So I will replace this phi m here in this equation. I will replace the phi m here. If I replace the phi m here, so my V1 RMS is equals to whatever this value is, root 2 pi f phi m will be, this will be n1 Im mu A divided by L into n1. So ultimately, right, ultimately I can directly say that n1 square Im by L into mu A is basically proportional to V1 by F. That is what I can comment about. So from here I can directly say that my here, right, Im will be constant, n1 will L will be constant. They have not mentioned anything about L. L is assumed to be constant. Area will change. V1 is constant. F is constant. So I can take the ratio now. Okay. So if I take the ratio, that is n1, like this is the initial value, and if I take the ratio of the final value, so final value will be n1 whole square dash into Im dash divided by L dash mu dash A dash. That should be also proportional to V1 dash F dash, and V1 dash and F dash are both same. Okay, so if I take the ratio now of these two things, so what I will get is, this will be n1, this is square, right? So n1 divided by n1 whole dash whole square Im dash will not change, magnetizing component current will not change, L dash also will not change, so those will automatically get cancelled. Mu dash also nothing is commented about, so it is not changing, but A dash is changing. So A dash is actually half, A is actually 1/4 of the previous value, so A dash will be A by 4, so this will be A divided by A by 4, and the right hand side also is 1 only, because it is just a like proportionality constant. I can write this equals to K, like some constant K into V1 by F, and this is also some constant K into V1 by F. Okay, so basically K will get cancelled, and V1 dash and V1 are not changing, F dash and F are not changing, so this will be 1. So from here I can directly comment that my N1 dash will be equals to basically it will be N1 whole square. So right, I can take this A will get cancelled, I can take the whole under root, so this will be N1 divided by N1 whole under root, so this will be 1 by 2. So N1 dash will be 2 into N1, so I have to double the number of turns from the previous value, so I have to double it. So what are they asking? The factor by which the number of turns in the primary should change to maintain the same no load current, so I have to double it, so it will be C. Okay, because I have to double the number of turns to keep the same no load amount of current. Let's do the next question. So these questions actually get asked. Okay, two transformers of same type made from same grade of iron and conductor materials are designed to operate the same flux density and current density. However, the linear dimensions of one transformer are twice those of other in all respects. What is the approximate ratio of their kVA ratings? Okay, what is the approximate ratio of their kVA ratings? So that is what they are asking. So there are two transformers which are of same type. So if they are of same type, that means their mu r will not change, or reluctance also reluctance can change if they are changing the dimensions. Same grade of material, so mu r will not change, right? Mu r will be same. So again, let's write the things. So if they are of same material, so this is again initial, and this is final. So if they are of same material, so my mu will not change. And they're telling me that they are designed to operate at same flux density and current density. So if they are designed to operate at same flux density and current density, that means my Bm also will not change. Okay, current density means my J will not change. J. So J is the current density. J is equals to what? J is equals to I by A. This will also not change. I by A will not change. Okay. However, the linear dimensions of one transformer is twice those of the other in all respects. So linear dimension is twice. So if what do you mean by linear dimension? So a transformer, right, has, this is the cross section basically. So the flux flows like this, right? So this is the cross section basically. This is the cross section. Okay, so this cross section can be written like this, some AB side, and of course another dimension is there, the width of the transformer, that is W. So these are the linear dimensions. So all the linear dimensions are doubled. So what will be happening to the area of the cross section? So the area of the cross section will be actually quadrupled. So if A has been increased to 2A and B has been increased to 2B, so basically previous area was what? Previously area was AB, and new area will be 4AB. New area will be 4AB. Okay, so area has been increased 4 times. So what will happen to the current? Current will be reduced basically. Current will be current has to also increase by 4 times, because they have to maintain the same current density. So A dash I dash. So if they have to maintain the same current density, that is I by A, so A dash is 4A. So this will be I dash by 4A equals to I by A. So I dash is equals to 4 times I. So current will be increased to 4 times. current will increase by 4 times. Okay, that is one point. Now what about the voltage? What will happen to the voltage? So if you understand that what have they told, to operate in the same flux density, okay, they will operate in the same flux density. So if they are operating in the same flux density, so what is my voltage equals to? Voltage V1 RMS is equals to root 2 pi f phi m into n1. So they have not talked about the number of turns, so I will assume number of turns is same. So it has to operate in the same flux density, so I will convert this formula phi m in terms of bm. Okay, so it will be changed to bm, so this will be bm into a. So phi m is equals to simply bm into a, that's it, right? Phi m is equals to bm into a. So my v1 RMS will be root 2 pi f bm into a into n1. Okay, so from here I know my bm is constant, bm does not change, but flux area changes, area is 4 times. So this is my initial. So if I just take the ratio of v1 dash RMS will be what? V1 dash RMS will be root 2 pi f dash bm dash a dash n dash n1 dash. Okay, nothing is mentioned about the number of turns. Assumption is number of turns remains same. Okay, yeah, number of turns remain same. So v1 dash by v1 RMS, basically, right, I have to find out what is happening to the voltage and the current, because they have asked me that what is the approximate ratio of the kVA ratings. So what is kVA? kVA is voltage into current, right? V into I. So for I have already found out the change in current, I just have to find out the change in voltage, so that I can directly write what will be the overall change in the kVA rating. So this is v1 RMS by v1. So this will be this will get cancelled, so this will actually be bm dash and bm are same because they are operating in the same flux density. It will be equals to a by a dash, sorry, it will be a dash by a, that's it. So a dash by a is what? 4. A dash by a is 4. So my v1 RMS, v1 dash RMS also increases 4 times, quadruples. Okay, this also increases 4 times, so this will be 4 into v1 RMS. So ultimately, if I have to find out the new kVA rating S dash, it is v1 dash RMS into I1 RMS. So this I1 dash RMS. So this is equals to, what is v1 dash RMS? It is 4 times v1 RMS into 4 times I1 RMS. Correct. So from here I can directly write that it is 16 times v1 RMS into I1 RMS. And what is v1 RMS into I1 RMS? So v1 RMS into I1 RMS was the initial kVA rating. So it is 16 times S. So actually S dash upon S becomes 16. So the change in factor is 16. Okay here. So 16 will be the change in factor by which the kVA rating of the transformer will change. Okay. Okay. So few theoretical questions. What happens if transformer cooling system fails? What will happen? If the cooling system malfunctions, basically it can lead to inadequate heat dissipation. So overheating will happen. There will be insulation degradation, and obviously the device can totally fail. There can be faults, all those things. So proper cooling is essential. So interview questions are there. So we were discussing about interview questions, because in the previous lecture we had discussed about the construction, right? So few interview questions related to the construction here I have done. Okay, so what are the consequences of interchanging primary and secondary windings of a transformer? If I interchange in the primary and secondary windings of the transformer, basically what will happen, there can be incorrect voltage transformation. So I am expecting that I have a transformer 1:4. I'm applying voltage of V1 here. I'm expecting 4 V1 here. What is happening is I have swapped, although externally I don't know that I have swapped the windings, but internally I have swapped the windings. So it actually it should behave as 1:4, but it is behaving as 4:1. So if I am applying some V1 voltage here, I will get V1 by 4. So that is a very bad thing, right? I mean, we are getting low voltage, we are expecting higher voltage, and if I flip it, let's say if this was supposed to be a 4:1 transformer, but it is working as a 1:4 transformer. It is working as a 1:4 transformer. So what will happen? If it is working as a 1:4 transformer, then basically this will become, this should have been V1 by 4, but I am getting 4V1, so that can damage, right, everything. So just be careful regarding that. So these were few interview questions. So now let's discuss about the losses in transformer. So whenever there is a device, right, there is a device and you're giving some input to the device and you're expecting some output of the device. Okay, in between there will be always some losses, because what is happening in the device, in the transformers, what we're doing in the transformer, although the losses will be very low in transformers, in DC machines it will be very high, but in transformers basically our transformer converts the electrical energy into magnetic energy, and then it converts it back to electric energy again at the secondary. Okay, so that is the thing, right? Like just examinations, you study for something, you study in your semesters, right? Study for semesters. So whatever you study, you will obviously not be able to replicate it perfectly in your answer script. There will be some losses, you will forget something. Okay, so you will not get 100 out of 100. It is very rare that you get 100 out of 100. Sometimes you can, but very rare. So I give some input to the device and there is some output, and in between there will be some losses. So my output will be the input minus the losses, or I can write it otherwise, flip it, that input should be, like I have to provide both, right? I have to provide the losses, the energy consumed due to the losses, as well as the output, the energy that the output will take. So input will be equals to output plus losses. Okay, so in transformer there are mainly four kind of losses. First is copper loss, that we have already discussed. I have also derived the expressions, I square r. If you remember, I have already discussed about the expressions here, right? I will not derive it, I will directly write the expressions now, because in the previous lecture we had already derived all the expressions, previous to previous lecture, if I remember, previous to previous or some lecture, right? So already had derived this. Iron loss is the core loss component, in which two losses are there, hysteresis and eddy current losses. Okay, and third one is stray losses and L13 losses. So these are very low, less. Main loss components are these two components. Due to these two components, the losses are the highest. Okay, so let's first discuss about the copper loss. So copper loss, very simple. We had already previously discussed that I have my windings here. So some current is flowing through the windings. This winding will have some resistance. So of course, there will be loss. So winding will have its resistance. Let's assume as R1. So current I1 is flowing. So there is a loss of I1 whole square into R1. Very simple, copper loss. So copper loss, basically R1 winding resistance will not change, although if temperature is varying, resistance will be changed slightly, but very minimal. So my copper loss, right, PCU is proportional to the current whole square. Copper loss is proportional to the current whole square. Okay, so we had already previously like derive all this expression, if you remember, that we had bring this back here. And what is the overall winding resistance? So if I approximate it further, if I want to approximate it further, I can either take this here or take this here. So the approximate model will be that this is not present at all, right? This is somewhere else to measure the current, because current I2 dash will be very large compared to IO. So this two can be in series. All these I have described previously, explained previously. So I am not explaining you in depth here. All these have been discussed already. So from here directly, the overall copper loss due to both the windings, copper loss VCU, the absolute value will be I1 square R1 plus I2 dash square into R2 dash. Okay, so we had derived this previously. If you remember, it was equals to I1 whole square RO1, or it is equals to I2 whole square RO2. Okay, and we had derived the what is RO1? RO1 is basically yeah, because I1 and I2 dash are same only, right? I1 and I2 dash will be same, they're in series. So RO1 is R1 plus R2 dash referred to the primary, and RO2 is R1 dash plus R2. Okay, so total loss remains same if you revert to the secondary or primary, it does not matter. So what is full load copper loss? If you remember, there was a term known as full load copper loss. So it is referred here, or if I refer everything to the left hand side, it will not make much of a difference. This we had already discussed previously, so I am not explaining you here, right? We had already discussed. So what is the full load copper loss? Full load copper loss, CUFL, if you remember, it was IFL, full load current whole square, into RO1. Okay, if it is in the primary or if it is in the secondary. One more thing, if you remember, that how will I represent this, like if this resistance is there, right? So this full load current, depending on which side I am, this is FL1 if I am at the primary side, this will be IFL2 if I am on the secondary side. Okay, full load current in the secondary side, depends which side I am in. Okay, now how do I measure the copper loss at different loads? Okay, this was the full load. So at different loads, my current, right, let's assume that because if load changes, what is the important point? This is a load, right? Load. Okay, the voltage across the load will be fixed due to the secondary winding of the transformer, that is V2. So if I change the load, what will change? If I change the load, the impedance will change. Impedance will change. If the impedance changes, voltage is fixed, so current will change. Correct? So basically we vary the current, and if current varies, then the copper loss also will vary. So that means if load varies, copper loss also will be varied squared. So my current I is some x of I FL. Okay, so full load current, this, right, PCU I can write copper loss at different loads. PCU will be equals to x into IFL whole square into R1. Okay, or RO2, whatever, like into R I will write, it depends in which side you are referring to. So basically this will be x square into PCUFL, full load copper loss, and my x, right, x will always lie between 0 to 1. Obviously x cannot go beyond 1 and less than 0, because like my current, right, I will never go above my rated current, I will always be lower than my rated current, correct? That's why x will be between 0 to 1. Okay, so at any particular load, the copper loss actually will be x square times the full load copper loss. Understood? Copper loss will be x square times the full load copper loss. Okay, now all these are done. So copper loss occurs in the winding due to internal resistance. When current flows, it dissipated, it is proportional to I square R, can be minimized by using low resistance winding material or high conductivity material as coppers. Okay, so that was about the copper loss. Now these are done. Okay, these are done. Now we will discuss about the per unit copper loss. So my PCU is equals to x square into PCUFL. Correct? So what is the per unit copper loss? So if you remember, in the previous lecture only, I had derived what is the per unit copper loss. So PCU FL per unit, full load per unit copper loss was actually equals to RPU, whichever side I am in. If I am in RO1 PU or RO2 PU, it does not matter. Okay, both are same only. RO1 PU and RO2 PU is same. So this I have derived in the previous lectures, so I am not deriving it over here, I am just writing down the results. Okay, now copper loss at any load, per unit copper loss at any load, what will be the PCU at any load? It will be basically x square, because now what will happen is like what is the uh, so right, basically if I write the copper loss at any load, it is x square into PCU full load, that is I FL whole square, sorry, basically it is I square into resistance, I square into resistance, correct? So at any load, okay, and I know that my I is equals to x times IFL, correct? So what will be the per unit copper loss? Per unit copper loss will be equals to I square by R, right? I square into R divided by x IFL. So this will be I square R divided by the full load copper loss. So because I want to write the base value, so this will be I square FL into sorry, this is I square FL into R base, right? This is I square FL into R base. So basically what will happen? This will be what? I square divided by I square FL, that is I divided by IFL whole square, that is x square from here, and R divided by R base will be simply RPU. This I have derived. R divided by R base will be RPU. This I have derived in the previous or previous to previous lecture. Okay, this I have derived. So the per unit copper loss at any load will be actually equals to this value. So this is, you don't need to remember it, but it's good to know. It's good to know what are the expressions. So PCU per unit will be x square into RPU. Okay. So that is the case over here. So yeah, this was about mainly the copper loss. So we have finished the copper loss. So we'll delete these pages. So here, right, whatever I have told you, that same thing is written over here. R equivalent is basically the equivalent resistance either in like R equivalent can be either RO1 or RO2 depending on which side I am in. Okay, per unit system will be this value, and per unit copper loss, this is PCU PU. Actually this is okay, this is PCU, absolute value of PCU, and if I want to write the per unit value of the copper loss, PCU PU, per unit value of the copper loss will be x square into RPU. That's it. Okay. So now let's discuss about iron loss or coal loss. Okay. So these losses occur in the core of the transformer and are independent of the load current. Hence these are called as constant losses. So these actually do not depend as on the load current. So these losses actually depend on the load current. That's why these are known as the variable losses. These are also known as variable losses. Why? Because it depends on the load. If the load is higher, then load current will change. Current will be higher. If the load is lower, load current will be lower, so copper loss will be lower. So these are like copper losses are called as ohmic losses, also called as variable losses. But iron losses are called as independent losses, that is independent of load current. That's why they are called as constant losses. Briefly, I have described why hysteresis happens. Briefly, I have described why eddy current happens. So in this core, flux is flowing. Due to that, voltage will be induced inside the core, inside the cross section. Due to that, in that loop, a closed loop will be formed because this is just a metal. So metal is a conducting path. So there is a closed loop formed. So basically, current will flow, and due to that current, there will be eddy current losses. Okay. Sorry for the interruption. Actually, my fan was making so much of noise. Like there is an issue with the fan, so I had to change my studio. I have to go into some other room. I have to change the fan. So yeah, for 1-2 lectures, like the studio will be different, so my face can seem a bit different. Okay, so we have to do everything, like all these things also we have to manage. So yeah, we were discussing about the iron loss. So I had already discussed about bit about eddy current loss and hysteresis loss, how it happens, what happens, eddy current is there, how it happens. So now we will discuss about the bit about the hysteresis loss, how it is dependent on different parameters. Also we will discuss how can I find out the hysteresis loss if the BH curve is given. If the BH curve is given, how can I find out the hysteresis loss? That is what we will discuss. Okay, so we already know like when alternating magnetic field magnetizes and demagnetizes the core, there is repeatedly of changing of the flux, right, in the core. Due to that, there is realignment of the dipoles. Due to that, there will be friction between the dipoles. Due to that, there will be losses. That is known as the hysteresis loss. Now, the hysteresis loss is actually proportional to the area enclosed by the hysteresis loop of the cone material. So, hysteresis loss is proportional. So, P hysteresis is proportional to the area of the hysteresis loop. How is it proportional? I will briefly discuss about that as well. Okay, and the formula for hysteresis loss is given as this. Do you have to remember the formula? It would be best. Okay, I very rarely say that you remember something, but this one you have to remember. Why you have to remember I will explain. Okay, so this one you must remember, and the eddy current loss as well. So few things to notice here for the hysteresis loss, that my hysteresis loss actually depends on the maximum flux density on the core. So if the flux density is higher, that means I am somewhere here, so there will be more hysteresis because I will go here and here, so the area will increase, basically the area of the loop will increase. So as the flux density increases, the hysteresis loss also will increase. It depends, it is directly proportional to the frequency. So why is it proportional to the frequency? If frequency increases, that means the current is alternating at a faster rate. That means the field is magnetizing and demagnetizing at a faster rate. So if there is more magnetizing and demagnetizing, of course there will be more hysteresis loss. So as the frequency increases, so hysteresis loss will also increase. It is linearly proportional to the frequency. So I will write few things here. Okay. So my pH, hysteresis loss, is linearly proportional to the frequency. My pH is proportional to the flux density, but actually, right, it is not directly proportional to the flux density. It is Bm raised to power x. What is x? X is a constant known as Steinmann's constant. Now actually x depends on material. So x depends on material, Now in the latest books, IEEE has suggested to take x equals to 2, because as material will vary, then the x also will change, because different materials have different magnetic properties. That's why if by default nothing is mentioned about the Steinmann's constant, you will choose x to be 2. That means my hysteresis loss will be proportional to the square of the flux density, maximum flux density. Okay. Also my hysteresis loss is proportional to the volume of the core, right? Because the last term, if you see the last term here, right, this is the last term, V. So V is the volume of the core. So that's how hysteresis loss is proportional to the volume of the core as well. Okay, it is proportional to the volume of the core. If the volume increases, there will be more hysteresis loss because more flux is flowing through the core. Okay, flux density is same, so naturally hysteresis loss will also increase. So roughly I will discuss about that as well. So one thing, like how is it proportional to the area of this curve, area of this loop? How is it proportional? So what is the power delivered to the material? The power delivered to the material, the power delivered to material, it will be basically the product of voltage and current. So my V is equals to d phi by dt. Okay, I know this according to Faraday's law, total flux linkage, or it is equals to n d phi by dt, right? D psi by dt or n d phi by dt in the coil. I'm talking about, right? In the coil. And what is I? I is simply I only, right? I is simply I. So what is the power delivered? P of t. P of t will be V into I, that is, it is n d phi by dt into I. So what is Ni? Ni is the MMF. Right? mmf, and this is d phi over dt. N into I is mmf simply. Okay. Now what is the energy actually? What is the energy? So energy, if you remember, energy is integration of power with respect to time. So it is basically equals to integration of Ni or mmf d phi dt. Okay. So basically it becomes Ni d phi basically. Okay. And what do I know? I know that this equation I know, right? So I know H into L according to Ampere's law is equals to N into I. This I know. So from here Ni is equals to H into L basically. So this can be replaced with H into L. And what is phi? Phi is equals to B into A. So d phi will be, A is area is constant, as assumption is of course area of the cross section is constant. So this will be A into dB. Okay. So here this will be H into L into A into dB. So what do I get is, this becomes, what is length, like this is length into the area of the cross section. So what is length into area? Length into area is simply volume. Length into area is simply volume. So the energy that is consumed from the hysteresis loss is volume into integration of H dB. So this is the energy consumed in hysteresis loss. Okay. So this is the energy consumed in hysteresis loss. So I hope you have understood this basic point, that what is my hysteresis loss? It is the area of the HdB. So HdB, if I want to integrate, it is not area like this, not this area. The area is like this, HdB. So HdB will be this area, right? This area. Okay. Not this area, not this area. It is this area, H into dB. Okay. So that's how we get the formulae for hysteresis loss. Okay. So what will be energy density? Energy density will be directly integration of the this hysteresis loop only. So energy density is what? Energy density is energy upon volume. Okay. So basically it is this energy upon volume. So volume will get cancelled, only integration of H dB will be left. So if they are asking energy density, that means it is independent of the volume, just you have to find out the area of the BH cup, that's it. So what is the area? Area is this small rectangular strip, this area, right? This area. Now you might have a question, sir, you told that the hysteresis loss is the area under the loop. You did not say that hysteresis loss is this whole area. Why are you saying something like that? I will explain. Okay. So let us take few points in the hysteresis curve and then we will understand this even better. Okay. So for that I have taken few points here. This is the graph actually. Graph is here. Graph is with me here. Okay. Yeah. So let's discuss here only. Let's discuss here only. Okay. Okay. So these are the different points. Now I have started from point O. Okay. So I will calculate the like overall energy consumed in the hysteresis loss is I want to calculate the power. I want to calculate the power consumed. Right. What will be power equals to? Power will be equals to energy per unit time or energy consumed in one cycle. That is also my power. Okay, that is also my power. So that is what I will calculate. Okay. So power is energy consumed in energy consumed in one cycle. That is what my power is equals to. Okay, so I will calculate in this whole cycle how much energy is being consumed. Okay, so let's start from 0 to A. If I move in the first one, so my overall energy consumed H dot dB in one cycle. I'm just talking about density for now. Volume is like a constant thing, right? Volume will anyways get multiplied. Assumption is I'm talking about energy density. At the end I can multiply by volume, that is no problem. Okay, so HdB will be equals to integration of different paths, right? I can break down it. So this will be HdB of the first path, that is O to A, then plus HdB from A to B, then HdB from B to C, plus HdB from C to D, plus HdB from D to O. So this will be the whole cycle, right? So let's first calculate for the first one. So for the first one, I am going from O to A. So what is H dot dB? So I have to choose a rectangular strip of dB length. So dB will be differential length like this in this direction, right? So the rectangular strip will be somewhat like this. Where are all the colors? Yeah, it will be something like this. This will be the rectangular strip. Okay, so this is dB length. So what will be the area? Area will be this whole area, right? This whole area. This whole area will be the area, correct? If I am going from 0 to A, so this is the whole area. Okay, got it? This is the whole area that I am calculating. Now this was the area. So this area is equals to what? This area is actually equals to, let me write this as some point, whatever this value is, this is the whole area. Okay, this is the first one, that is integration 0 to O to A H dB. Okay, yeah, this is the whole area. Okay, so this is a positive area. If this is positive area, if H dot dB is positive, that means what? Like integration of H dB is positive, that means the material is absorbing the energy. So material is absorbing energy, Okay, now what about the when I'm going from A to B? What is the energy consumed when I'm going from A to B? So for the part 2, going from A to B. So this time, right, if I'm going from A to B, this will be part 2. So this will be basically here. This, like I have to take, I'm going from A to B, so I'm going along this curve. So the dB will be here. Okay, so the area will be, if I just choose a color, area will be this color, this one. This is the area. Okay, previously this was the area. Okay, this whole thing was the area. Now this is the area. Got it? Okay, we got. And what is happening here? If you see what is happening, is basically, is it positive or negative? That is what we have to identify. So is the area positive or negative? So if you see here, right, if I'm moving from O to A, how is it positive basically? If I'm moving from O to A, my dB is increasing, right? dB is increasing, correct? Because I'm moving in this direction. dB is increasing, I'm moving in this direction. Okay, so dB is going in this direction. So dB is change in flux density is positive because my flux density is increasing, my magnetizing force is already positive. So that's why this is positive. So dB is positive and H is positive. So that's why the overall energy is positive. That means the material is absorbing the power. But if I am here, right? If I am here, if you see, yes, it is on the right hand side of the y axis. So H is positive. In this region, H is positive. But what about dB? If you see, I am going from A to B. So my dB, right? I am going downwards. I am going in the downwards direction. So dB actually is negative. dB is negative because I am going in the downwards direction. Although I am right hand side of the y axis, but H is positive. Yeah, H is positive. That is correct. H is positive because I am on the right hand side of the y axis. But my dB, change in magnetic field flux density, is reducing. It is negative. So dB will be negative. So if dB is negative, this area, whatever I will calculate, this will be a negative area. That means basically here, right, the energy is getting delivered by the material. So material delivers energy. Delivers energy. Okay. Now let's discuss about the third portion. If I am going from B to C, B to C. So again I will basically I will take this. So this will be from B to C. So if I am going from B to C, if you observe that dB is again increasing, right, because I am going downwards. So again I will choose a rectangular strip like this, okay, and my dB is negative because I am going from top to bottom. So dB is reducing basically. So it is negative. B is reducing. As B is reducing, dB will be negative. So I am going from top to bottom. So it is reducing. Okay. So I can directly write here that my dB is reducing, right? dB is reducing. So if dB is reducing, basically I can directly say H is, what is H? H is also negative, right? If I am going from B to C, I am on the left hand side of the y axis. So in this region, H is always negative. So H is negative, dB is negative. That means overall integration of H dB will come out to be positive. Again the same I will write that material absorbs power. Material absorbs the power. Okay. And can you identify what this area is? This area is this one, right? This area. Basically I am moving from here to here. So it will be this whole area. So what is this area equals to? This area is same as this area. This area is same as this area if the hysteresis loop is same. Okay. So basically what I can conclude that my H dB OA and H dB BC are same. Okay, if my hysteresis loop is symmetrical. If my hysteresis loop is symmetrical, it will be equal. Now let's come to the fourth one. Fourth one, I'm going from C to D. Okay, I'm going from C to D. So if I'm going from C to D, that means what? That means I'm going from here to here, right? So if I'm moving from here to here, that basically means I have to choose a rectangular strip here. Okay, and this will be my desired area. And if this is my desired area, what is happening to dB? If you see, I am moving from here to here, that means I am going upwards. That means my flux density is increasing. That means my dB will be, basically I am moving upwards. So my dB will be greater than 0. H, again I am lying in this region only, that is left hand side of the y axis. So H is negative. So integration of H dot dl will again be negative. Same thing that happened in the second point, that material delivers the power. How does it deliver? Because it has some residual flux. That's how it delivers the power. Okay. So material delivers the power. Another important point, this energy and this energy are equal. I mean this energy from, if I am moving from C to D, H dot dl, this energy, and if the hysteresis loop is of course symmetrical, if I am moving from A to B, this will be equal to each other. Okay. Okay, now let's come to the last point. Last point is this one. If I am moving from D to O, if I am moving from D to O, what is the energy? If I am moving from D to O, the energy, right, the fifth point. So if I am moving from D to O, the energy, right, okay, the energy will be basically this one, correct? This will be my strip and this will be the energy consumed. Okay, so I can directly say that this will be energy, and here what is happening, here my dB is positive, the change in magnetic field is positive, so it is greater than 0. H is also positive. Okay, so H dot dl also will be positive, that means material will absorb the power. Now the important point to note here is what is happening. So if you observe, in the case 1, this was the whole area, in the case 2, this was the area and it is actually negative. So I am subtracting this area from this whole area. So how much will the resultant area be? This area, correct, this area. Same thing is happening in the case 3. In case 3, this is the whole area, okay, and in case 4, this is the area and it is negative, so it is positive. So actually I am subtracting this area from this whole area. So how much area I have? This whole area. Okay, so I have already this area and this area. Okay, what is the left area? This much, and this is what the final area. So from here we derive that our hysteresis loss or the power loss pH will be proportional to area of the hysteresis loop, and because all this was energy density, remember all of this was energy density, right? Whatever we have discussed, it was all energy density. Okay, so I have to multiply a volume as well. So this whole thing will be multiplied with a volume. Okay, this whole thing will be multiplied with a volume. HdB, whole thing will be multiplied with a volume everywhere. Okay, so everywhere we discussed about volume. So my power loss in the hysteresis, my hysteresis power loss will be proportional to the area inside the hysteresis loop into the volume of the core. Okay, so very important point to note here. I know someday they will ask a question, and generally no one like derives it and says it, just they say that this is the hysteresis formula and that's it. Okay, very important point to note here. So this is the main conclusion. Okay, got it? This is the main conclusion. I hope you have understood this point. I have given you the formula as well, and how is the formula related? I have given you the, if the BH curve is given, then you will solve using these concepts. If the BH curve is not given, directly you will use the formula. The formula is what? Here. Formula is here. Got it? So that's how you solve for the hysteresis loop. Okay, I hope you have understood this basic point. So that is done. Now one more thing. There are many things for hysteresis loss. Okay, so one thing is that if there are two cases, so my hysteresis loss, if I go by the formula, hysteresis loss is proportional to Bm square F. Now I know in turn my phi is proportional to V by F, if you remember, right? Phi is proportional to V by F, or if the area is constant, then my Bm will be proportional to V by F, assuming that the area of the core is constant. Area of the core is constant. Okay, so that is what my pH is equals to. So there are two cases here. Case 1, okay. In the first case, if my V by F is constant, if my V by F is constant, that means my flux phi m will be constant. That means my area will be, that means my Bm will also be constant. Bm will also be constant. If this is the case, that means my pH will be only proportional to the frequency. It will not be, it will be independent of flux. So conclusion is independent of Bm, basically flux density. Okay. The next point, if my V by F is not constant, if it is not constant, if it is not constant, that means my phi m is not constant, that means my Bm is equals to what? Bm is proportional to V by F only, if area is constant. So I can replace my Bm in this equation, okay, and assumption is like I am choosing my Steinman constant to be 2, okay, that is what IEEE recommends, so I will choose 2 only. So my hysteresis loss, right, will be actually proportional to Bm whole square by F, so that is V by F whole square into F, because Bm is proportional to V by F. So from here I can directly say the hysteresis loss will be proportional to the voltage whole square divided by F. Okay, so where V is the voltage and F is the frequency. Okay, so yeah, that is it about, basically that is it. Got it? So two things are there. So hysteresis loss is proportional to the volume of the core. So if the core is made thinner, then there will not be any problems. If the core is made thinner, then there will be less loss. So this is actually one of the reason we use steel, because steel is actually thinner. Like steel can be used, like the property of steel is that it is very strong, very rigid material, even if it's thin. So that's why steel is used. Okay, steel is used as the core material. Got it? So that was about the hysteresis loss. Now let's discuss about the eddy current loss. What will be the eddy current loss? So again, eddy current loss, I will not derive the expression, not that important, but what you have to understand is my eddy current loss will be this value, okay, where eddy current loss equals to Ke, the constant, into Bm square. So it is also proportional to the square of the flux density. It is proportional to the frequency square. Hysteresis loss was directly proportional to the frequency. Here it is proportional to the frequency square. It is proportional to the thickness of the material. So T is the thickness of the lamination of the material, and V is the volume of the core. So it is obviously dependent on the volume. So I will not derive the expression, but basic thing you understand that my eddy current loss is actually proportional to the thickness of the core. So somehow my actual core is this, right? Actual core is this. So somehow if I can reduce this thickness, this is the thickness of the core, right? If I can break this thickness down into smaller laminations like this, so the core is there to provide rigid support. What we do? We provide small laminations. Small laminations. So due to which the effective thickness is reducing, due to which the eddy current loss reduces, because the core resistance is increased somewhat. Okay, so basically what are the key points? Key points is my eddy current loss depends on the thickness. That's why we use thin insulated plates instead of a complete solid core. We use thin insulated plates, okay, steel plates, thin insulated plates, thin insulated plates, okay, instead of solid iron. We don't use a complete solid slab of iron, we use thin insulated plates. Got it? So what is my eddy current loss proportional to? So eddy current loss actually depends on the flux whole square, magnetic flux density whole square. My eddy current loss depends on the frequency whole square. Of course, it depends on the thickness whole square again. This formula you have to remember, right? Thickness whole square again, and it depends on the volume. This we already knew. So what is same for hysteresis loss? Also, it depends on the volume of the core. For eddy current also, it depends on the volume of the core. But here new things are, it depends on the thickness whole square and it depends on the frequency whole square. There hysteresis loss was depending only on the frequency. Okay, so yeah, that was about it. So yeah, that's about the eddy current loss basically. So we will solve few questions and from there we will understand how to solve this kind of questions. Okay, so now again there are two cases here. Again there are two cases. So what is the first case? First case, like my PE is basically proportional to, like if the core dimensions are constant. Okay, so obviously once you have made the core, you will not change the core, right? Core dimensions. So assuming core dimensions to be constant. So if I assume core dimensions to be constant, then what will happen is that what is my actual PE? PE will be proportional. It will not depend on volume of the core. It will not depend on the thickness because those are constant. It will only depend on the what do you call? It will only depend on the flux density whole square, and it will depend on the frequency whole square, and nothing else, right? Only that, these two. Yeah, only these two. One more thing I just wanted to say, that let's assume that if this was not actually squared, if this is x only, how will you solve? If this is x, right? If this is x, this will be bm x raised to power f. So ultimately the value here, it will change basically. This will not be square, this will be v by f raised to power x into f. So ultimately, right, the value here will come out to be, value here will come out to be v raised to power x divided by f 1 minus x. Okay, that is the only modification that you have to do. Got it? Okay, now let's come to here. So again the same thing, right? If my v by f is constant, that means it will not depend on the flux, because then bm will be, phi m will be constant, that is phi m proportional to bm will be constant. So my PE will be proportional to bm is constant. So it is only dependent on frequency whole square. Okay, eddy current loss is only dependent on the frequency whole square. Now if v by f is not constant, if it is not constant, I will replace, like my phi m will be what? Phi m will be proportional to bm, it will be proportional to v by f if core dimensions are same. Okay, so I will replace here in this equation v by f. So actually my eddy current loss is proportional to v by f whole square. Here there is no Simon's constant, it is fixed that it will be squared only, because power loss, right? Power loss is v square by r, something like that. So it will be f square. So actually my eddy current loss is proportional to the only the voltage square. It is independent of the frequency if v by f is not constant. Okay, so that is the key point that you should take, because questions will come from this only. Questions will come from this particular zone only. Okay, now let's discuss about stray losses. So these are the losses that are very low in value than the eddy current and hysteresis loss, but this still occur. So these are assumed to be like these losses generally depend on the induced eddy current. Stray losses occur due to leakage flux, which induces eddy currents in the transformer tanks, bolts and other metallic parts. So if you remember that we had two components of flux, right? One was the core component of the flux that went through the core, another one was the leakage flux. Now of course what is happening is that transformer is just not a core and two windings, right? There are so many things in the transformer which we discussed, like bushing is there, then there is conservator tank, then there is the Buchholz relay, then there is the transformer oil that is flowing. So due to this flux, time varying flux, those also will have a eddy current, right? There will be induced EMF, and due to that there will be eddy current, and there will be losses basically. So this stray losses are the losses that is caused due to the leakage flux, which induces eddy currents in the other components of the transformer other than the core. Got it? These losses are generally very small but can be reduced with proper designing and shielding. Okay, so its location is actually uncertain. It can happen anywhere in the transformer. There are so many materials because leakage flux will flow through any path, so losses can happen anywhere. Okay, it depends on the load current. Since leakage flux is proportional to the current, because what is flux? Flux is proportional to current, right? Flux is proportional to current. Leakage flux is not fixed actually. Whatever the induced voltage here I have, if that is fixed and the frequency is fixed, then the maximum flux in the core is fixed. But the leakage flux actually is load dependent. You should know this. Phi leakage is load dependent. Okay, load dependent. So if it is load dependent, then the eddy currents also will be load dependent. So actually stray losses depend on the load. So that's why these are called variable losses. These are not called constant losses like the iron losses, okay, which we discuss in hysteresis and eddy current loss. Got it? Okay, so there are many kinds of stray losses. One is the iron loss, so occurs in the transformer tank and the core due to induced EMF from the leakage flux. Another, how to minimize this, we can use aluminum tanks that are paramagnetic materials, so that whatever the leakage flux flows, very low amount of flux flows through the core material instead of ferromagnetic materials. Instead of using ferromagnetic materials that actually support good amount of flux, because those materials do not need to support flux, right? Those are used for other purpose. So that's the thing. Then we have stray copper loss, occurs within the windings due to non-uniform current distribution caused by leakage flux. Okay, so mainly this is depends on the load, and this is very small, like 0.5% of the rate, and even smaller, 0.1% of the rated power. Okay, so generally it is neglected. Then the next loss is the dielectric loss. What is dielectric loss? So if you remember that I have these windings, right, and LV windings and HV windings are placed very near to each other. That is what we have discussed in the construction. So like there is some insulation, but insulation also will have some leakage current or something. So some leakage current flows through the insulation, if you remember, right, if you have studied the electric field intensity, all those things. So due to those leakage currents, there will be some energy loss. So dielectric loss occurs in the insulating materials used in transformers such as solid insulation and insulating oil. It is due to dielectric hysteresis and leakage currents in the insulating material. So as I mentioned, there will be some leakage current between the insulation. Although you have provided the insulation, still there will be some leakage current. Okay, there will be some capacitance, and through that capacitance some current will flow. So there will be some leakage current. Okay, this is actually independent of the load current because it is voltage dependent. So higher the voltage, the higher the chances of insulation failure. So it is independent of the voltage. That's why it is called as constant loss. It depends on the voltage and frequency. Why voltage? Because if voltage is higher, electric field will be higher. If electric field is higher, there will be dielectric background, due to which losses can happen. If frequency is high, that means this capacitance, dielectric capacitance will be lower, so more current will flow through this. So there is higher chances of losses. Got it? So this causes heating and all those things. How can I minimize? We can use high quality insulating materials to minimize it and maintain proper insulation condition. Okay, so that there is no degradation, because if you know anything about insulation, even if there is some moisture, there is some dust in the insulation, right, that will degrade the insulating material actually. Okay, so all these things you have to take care of. So what are the key takeaways? The two major losses what we have studied is the copper loss and the coal loss. Okay, so these are the mainly two losses which you will be used in calculation. Stray losses and the dielectric losses will be given to you either, or if they are not given, then you will assume them to be zero. Okay, during efficiency calculation, dielectric loss and stray losses are usually neglected as they are relatively small. Okay, as they are relatively small, they will be generally neglected. Copper loss is variable while coal loss is constant. Lamination of the core helps in reducing the eddy current loss. Okay, so So my P core will be independent of I. Okay, and copper loss is variable, that means P copper is function of I. So load changes, the copper loss will change, but the coal loss will not change. Okay, so same thing is written over here. Copper loss is a variable loss, stray load loss is a variable loss. Okay, coal loss is constant, dietary loss is constant. Okay, now let's briefly discuss a bit about the transformer ratings. What do they tell us? Transformer rating. So volt ampere rating we have already discussed, and why do I define in terms of volt ampere, not kilowatt? Because my transformer actually transfers both the energies, the reactive energy and the active energy. That's why it is written in volt ampere, because it transfers both reactive and active energy. Of course there is some losses that I do understand, but as it transfers both, that's why the rating of transformer is in kVA or MVA. Okay, frequency is usually 50 to 60, and there are two types of transformer depending on the phase. So it is single phase or three phase. Okay, so three phase we will study later on. Currently whatever we have studied is for single phase transformer. And the generally, right, the windings are not actually called secondary and primary, they are called LV and HB to better understand the windings. Okay, because primary and secondary does not give us any information. HB tells me that HB winding will have higher number of turns, LV winding will have lower number of turns. Okay, so yeah, I hope you have understood this basic point. Same thing is written, why the rating is in kVA, and why is HV winding and LV winding named, not primary and secondary. Okay, the reason is also mentioned over here. So very easy, like any transformer, right, can work as a step up or step down, because it depends on which winding I'm connecting the voltage. Okay, just you should not go out of the rating, that is the important part. You should not go out of the rating. So one more important point is the conductor thickness and current. Okay, on the LV side I know like kVA rating is constant, so VI is constant. So on the LV side voltage is reducing, so current will be what? Current will be higher. So if current is higher, I will need thicker wire, high current. And on the HV side, the voltage will increase, high voltage, so the current will reduce because kVA rating is same. So current will be reduced, so I will need thinner wire, I will not need thicker wire. Okay, so while designing a transformer, this is also what you need to take care of. So LV winding will be bulkier and more massive than HV winding, although HV winding will have higher number of turns, but LV winding will be more thicker, so hence it will be more bulkier. So this is the practical aspect of LV, HV windings and all the transformers. So we have completed our losses topic. In the next lecture we will solve all the assignment questions on losses. Thank you for watching, and I will see you in the next lecture. Until then, happy learning.